Hi, good morning. Today we will be continuing with lecture. Last week was all about chapter 1 and conversions, and this week will be about chapter 2. Chapter 2 is about force vectors. And so let's go over a few definitions. So something that is a scalar, or you might call it a magnitude, is some number. Okay, it's just a number. So for example, if I gave you like the mass or a time, it would be just a number. Now, by contrast, if I had a vector, then that vector has a magnitude, but it also has a direction. So that's something like a force. So the force cannot just be a number, but it's also what direction it's being applied. So if I were to draw a vector, the magnitude would be represented by this length that I drew it. So that would represent the magnitude. And in reference to like a horizontal line, the direction would be whatever that angle is. We would label this point right here the tail, and this point right here the head. And let's say I wanted to name it vector A. I would write it like this, A with an arrow on top. Vector A. If I want to multiply vectors, so vector multiplication. Let's say I defined this as my vector A. Then 2A would be twice as long in the same direction. Or negative A. The negative sign changes the direction it's pointing. Or if I wanted to scale it down and change it, negative 0.5A. So the key is some scalar, so a number, any scalar, like scales up or down, right? It changes the size or the length of the vector. And a negative sign changes the direction. Questions so far? Okay, let's talk about vector addition. If you had, let's say, define this as vector A, and then you defined this as vector B, if I wanted to add them together, I would take vector A, okay, take vector A and put vector B at the end of vector A. And the result would start where I started and end where I ended. And we would call that our resultant force. So when we're adding vectors, we have to add, as they call them, head to tail. Okay, so you see, I took the head of A and I put it next to the tail of B in order to add. The resultant vector it starts at the tail of A, so the tail of your first vector, and ends at the head of B, the last vector. So think of it as you going on a hike. So if you went on a hike and you started at the beginning where A started, you would walk along A, and then maybe you took a right turn and then you walked along B, right? The result is you started at A and you ended at B. So that resultant force shows where you started and where you ended. Okay, so this is called the resultant vector. And so you should make a note that vector A minus vector B is equal to taking vector A and adding the opposite direction of vector B. So what I mean by that is if instead of addition, I wanted to do subtraction, then really what I mean is flipping around vector B and adding it. Okay, so that's what vector B is, like negative B. That's what I mean. So you're adding a negative B, which is going the opposite direction. So then if you were to draw it, you would take vector A, take vector A, you'd take your negative vector B, connect to where A ended, right? And draw your resultant force from the beginning of A and the end of B. Okay. Questions about that? Yes, Deepak.
So you draw every vector starting from the head. So if you had a third one, we would draw it from the head of the B vector. Correct?
Yes.
Okay. Will there ever be a scenario where it doesn't?
No, you always connect your head to your tail.
Okay, thank you.
Mm-hmm. Other questions? Okay, let's talk about vector components. So let's say we are in an XY plane. And we have drawn our vector, force vector A. We'll call it force vector A. Force vector A can be made up of two forces, one going directly to the right and one going directly up. Do you see how adding those head to tail completes the force vector A? It's almost like making the force vector A as the resultant force of those two individual components. So we could call this, for example, FA only in the X direction and FA only in the Y direction. So when you add, force vector A is made up of FAX plus FAY. So the key here is that vectors can be broken down into their components based on whatever your defined axis is. Questions so far? A little bit of trig review. Everyone loves trig. Let's say you have some sort of generic triangle. And let's label this side A, side B, side C. The angles across from the big sides are the little angles A, little angle B, little angle C. So this is any generic triangle at all. You can use the law of cosines. Who remembers what the law of cosines is? Just keep that one in your back pocket. You remember law of cosines? Rolls right off the tongue. If you're trying to solve for side C, then you would take the square root of side A squared plus side B squared minus 2 times A times B times cosine of little angle C. You knew that, right? It's all coming back. That's for any generic triangle at all. Now, law of sines has to only apply to what type of triangle? Oh, wait, no. Law of sines can still apply to any generic triangle. Sorry, I was getting ahead of myself. Who remembers what law of sines is?
Sine A over angle A equals sine B over angle B, and then equals sine C over angle C.
Yeah, you're on the right track. And it doesn't really matter what's in the numerator or denominator as long as they line up. But it's side A over sine of angle A, or vice versa. So sine of angle A can be on top over side A on the bottom, but it's the sides and then sines of the angles. So equals B over sine of little angle B and C over sine of little angle C. So both of those apply. Law of cosines and law of sines both apply to any generic triangle. And where I was going is then the Pythagorean theorem, everyone's favorite. What triangle does the Pythagorean theorem apply to?
A right triangle.
Only right triangle. So we'll draw ourselves a right triangle here. So still, if this is side A, this is little angle A, side B, little angle B, and side C. Okay, so for the Pythagorean theorem, it must be a right triangle. Who remembers what the Pythagorean theorem is?
C equals the square root of A squared plus B squared.
Yeah, perfect. C equals the square root of A squared plus B squared. Okay, and in reference to this triangle, you can also use your trigonomic functions, sine, cosine, and tangent. So for example, what is sine of angle A? What over what?
B over
Opposite over hypotenuse.
Opposite over hypotenuse. What's opposite of angle A?
That's B over C?
Opposite of angle A.
Oh,
That's
A
A.
over C.
Correct.
A over C.
Yeah. So big A over big C. What is cosine of angle A?
B over C.
B over C, because that's adjacent, over hypotenuse. And what is tangent of angle A?
A over B.
A over B. And by contrast, if you were going to do sine of little angle B, what do you get?
It's going to be A over C.
So opposite of little angle B is what side is it looking at?
B over C.
Very good. So that's going to be B over C. And what is cosine of little b?
A over C.
A over C. And what is tangent of little b?
B over A.
B over A. Questions about that so far? So if you're feeling pretty rusty, I would strongly suggest you do some review problems. There are review problems, and there's like basically a trig math review in the back of your book. So you can write this down that you should check out the appendix in the book. Whoops, in the back of the book for math review if you feel like you need it. Okay, and I'll even give you the pages 616 through 619. That gives you like some trig review and stuff if you feel like you need some trig review. Okay, up to you to do that. Be honest with yourself. If you're like, oof, I'm pretty rusty on this stuff, go do it. Because I'm assuming you know all this stuff. I'm assuming it's just like the back of your hand. You know it. You don't even have to think about it. Questions so far? All right, let's do some examples. So example 1, it says to determine the magnitude and the direction of the resultant force. And here is your picture. You have some sort of fixed surface with like a hook attached. And you have two forces pulling on this hook. One force is pulling this way, F1, and it has a magnitude of 100 newtons. The other force is pulling this way, F2, and it has a magnitude of 150 newtons. F1, in reference to the horizontal, is 15 degrees. And F2 in reference to the vertical is, if I can read my own handwriting, 10 degrees. So the way to add these vectors together is first by starting off with outlining your x and y axes. So let's just draw x and y to define our directions. You're going to draw F1 first, starting at the origin. Okay, F1 is 100 newtons. And it is in reference to that x-axis of 15 degrees. You're going to connect it, F2. So remember, F2 is 150 newtons, and in reference to that vertical, it's 10 degrees. And so your resultant force starts where you started and ends where you ended. And that's what we're looking for. Questions about how I drew that? Okay, so after I draw these pictures, what I like to do is just kind of look at the easy stuff and label what I can. So for example, I might drop a line down directly here. I might say, I know for sure that this angle is 90 degrees because that is a vertical down to a horizontal, right? Do you agree with that? So I just go for, as I call it, the low-hanging fruit. I go for the easy stuff. Well, I know this. I can draw that. I know that part. Okay. So then I think, building off of that, what's this angle? I can figure that out. What's that angle?
$65.
Try again. You're close.
Oh, 75.
Correct. Why?
90 plus 15 is 105. The 105 plus 75 is 180.
Yep. So all triangles add up to 180 degrees. So we know that this is 75 degrees right there. Okay. Let's see. What else do I know? I know that if I draw another horizontal line here, then this angle is also 90 degrees. What is this angle?
80.
Correct. Why is that?
Because 80 plus 10 is 90.
Very good. Okay, and so therefore, what is this angle?
$245.
Try again.
255?
Try again.
105?
Correct. Why?
I did that 105 plus the 75. It should be 180 degrees.
Okay,
It's a
very
straight
good.
line.
Yeah, so it makes one straight line. So 105 plus 75 is 180. So that's one way to look at it. Or you could think about going around an entire circle. What does everything have to add up to if you go around an entire circle?
360.
Very good, 360. So you'd ask yourself what's left after you've added all those angles up. So you see how you just need to start labeling it. You don't want to stare at it forever and be like, I have no idea where to start. There might be angles that you don't ever need, but they could help. And you might as well label it because you know that angle's 90 and that's 75. And you don't know if it'll help or not, but just dive in and start labeling what you do know. Eventually, you'll get to what you need. So for example, the reason I did that is, remember, we're trying to use law of cosines, and law of cosines has to do with that angle between the two vectors. So vector 1 and vector 2 have this angle, this complete angle from here to here, and now we know what that is. What is it?
$115.
Very good. Okay, so a few notes that you can write down to help yourself when you are labeling these pictures. All triangles add up to what? How many degrees?
180?
Yes, add up to 180 degrees. All circles add, let's just, sorry, we're doing bullets, so I'll do one bullet. All circles add up to what? Mm-hmm. $360 degrees. And then, like we said, label everything you can based on these basic principles. So use what you know after you've drawn it to label everything that you can. So if I were to simplify this picture, I essentially have a triangle where this is 100, this is 150, this we don't know, and this is 115. We have two vectors and the angle between those two vectors. Okay, so when we have two vectors and the angle between the two vectors, that's when we're going to use the law of cosines. So our resultant force is going to be equal to the square root of what?
Uh, 100 squared plus 150 squared minus 2 times 100 times 150 times cosine of 115 degrees.
Questions about how we got that? What do you get for the resultant force?
212.55
Okay, and what are your units?
newtons.
Very good. And remember, this is simply just the magnitude. It's that number. But we also need a direction because all vectors have a magnitude and a direction. So let's say so we have our triangle here. Let's call this unknown angle 1 and unknown angle 2. We already know we solved for R. It is 213 newtons. Now we can use law of sines because you can only use law of sines when you have the side and the angle across from it, side and angle across from it, right? And so now that we have that angle and the side, we can use it to find those other angles. So use law of sines. So let's say I wanted to use the 150 Newton side. What would I put it over?
Is it angle 1?
Yes, sine of angle 1. And if I wanted to use the 213 side, what do I put it over?
Angle 115.
Yes, sine of 115 degrees. Now be careful because this is a rounded number, so make sure you actually keep the number in your calculator. So use the number stored in your calculator and don't like round and then retype it in. Okay. Okay, so then I'll do a little quick algebra review. You're going to cross multiply. So you've got 150 times sine of 115 equals 213 times sine of angle 1. Questions about what I just did? Trying to isolate angle 1, we're going to divide by 213 on both sides. And then remember, we've got to do, to get angle 1 alone, we have to do sine inverse of both sides so that it crosses off and isolates angle 1. So what do you get for angle 1?
$39.8.
Questions about how we got that? Okay, so if we're zooming in on this resultant force, we know that it's 213 newtons. And there's this other force here, right, that was going like this. So we knew that its original reference angle here was 15 degrees, and we just solved for this angle right here, which is 39.8 degrees. So if you want the reference angle all the way to that resultant force, what is that angle?
54.8.
Okay, questions about how we got that?
I have a question on the angle one where it's 39.8.
Mhm.
I was wondering if I got 39.7, will that throw the next parts off?
Whatever you get, even if you're jotting it down to show your work, just keep it in your calculator and only round the final answer. If you're rounding your intermediate steps and then you go back and you repunch in those numbers, then yes, that could affect your final answer at the end. But if you keep whatever's in your calculator step by step by step, then you should line up pretty closely to the right answer in the end.
Okay, got it. Thank you.
Uh-huh. So this angle represents the direction of your vector. So your final answer is that you have your resultant force of 213 newtons at a reference angle from the x-axis of a total of 54.8 degrees. When someone tells you to find the vector, they mean both magnitude and direction, not just one or the other.
So technically, the magnitude would just be the resultant in this case, and then the direction is just the angle.
Yes, the magnitude is the newtons and the direction is the degrees.
All right, thank you.
Other questions?
Do we leave the final answer like the one you did on paper?
Yes, I would do that. It helps to be clear in grading at the very end. I would also accept just if you did it separately, if you just left, if you boxed your answer, this is my magnitude and this is my direction, then I would accept that. But it is kind of easier just to at a glance, to just draw it and have it all like that together. Other questions? Okay, number 2, it wants you to determine the magnitudes of F2 and FR. You're given that FR is vertical. So you have this fixed surface with some sort of handle attached. You have F1 of 200 pounds. F2, we don't know. But we do know these reference angles. This one's 45 degrees. And this one's 30 degrees. So look back at our last problem. What is the first step we should do?
We have to figure out all the simple angles.
Yeah, so we're going to start drawing it and label what we can label. So we've got our F1, which is 200 pounds. We have our F2, which we don't know. And we are given, remember it said that the resultant force is vertical. So we know that the start and end is a vertical line. So that's the resultant force. We'll call it maybe FR for resultant force. We can label what we know. We know that this 200-pound force has a reference angle from the horizontal of 30 degrees. We know that F2 has a reference angle from the vertical of 45 degrees. What should I do?
Since the 30 degrees, and then lines up with the vertical of the FR, I think you could say that that angle is going to be 60 degrees.
Perfect. So this is 60. What else can we label?
All the 90.
Okay, so we can drop here and we can say this is 90. Then what?
And then we can, the smaller triangle is 60, the top angle.
Okay,
That's
then
not-
what?
Then you can draw a horizontal line near the 45 degrees, and that'll make a 90, right?
Okay, sure. So we've got, you mean here, right?
Yeah, or
Okay.
also on the other side.
So that's 90, that's 90.
And then that outside angle, so we know the whole thing is 360. So it says 60 plus 90 is 150. 150 plus 90 is 240. 240 plus 45 is 285. And then 360 minus 285 is 75. So
Very
that's
good.
75 degrees, yeah.
What else can we label?
So 75 plus 60 is 135, and then 180 minus 135 is 55.
Try again.
55 degrees.
45.
45.
Mhm.
Yeah.
Questions so far? Okay, because we do have, check it out, we do have a side and an angle across from it. That means that we can use law of sines. So thank goodness, because that's a lot easier than law of cosines, right? So we can use law of sines. So help me set that up. What do I do?
But 200 over sine 45 equals, you could put F2 over cosine 60.
Sine 60. So
Sine
law of
60,
sines always sine. Yeah. Okay. And to get that to the other side in order to isolate F2, you're going to multiply by sine 60 on both sides in order to cross it off and isolate the variable. What do you get for F2?
$244.95.
Question so far?
So does it matter about the sig figs? So 3 sig figs is fine, correct?
Yeah, I don't care about sig
Okay.
figs.
All right.
But I do care about units, so make sure you know what units you're in. All right, let's use law of the sines again to try and solve for FR now. How do I set that up?
Isn't it just the same thing, but you switch out F2 and a sine 60 for FR and sine 75?
Oops. Okay. What do you get for FR?
$273.2 or 273
Units?
pounds.
Okay. So again, for your notes, all lines add up to how many degrees? Like, if you have a linear pair, what do they add up to?
180.
180. You could also use, remember, like alternate interior angles are congruent. Remember that? So we could have used that for, let's see, like, look at these, this one and this one. Those are alternate interior angles, right? So you could have used that to find the 45. So there's lots of different kind of principles you can use to solve for those angles. Questions about that problem? Okay, let's do number 3. So number 3 says FR must be horizontal by minimizing F2. Find the magnitude and direction of each. So you have a fixed support here with some sort of handle. You've got F1, 800 newtons. F2, we don't know. This reference angle is 60 degrees. This reference angle, we don't know. What should we do?
Can we start by making the y and x axis and drawing F1 in it?
Very good.
And then
So,
yeah.
yeah,
And then connecting
connect them.
F2. Yeah.
Good. So you've got F1 is 800 newtons. Connect F2. And it did say that FR must be horizontal. So we know that the final answer when you connect start to start and end to end is going to be horizontal. So that was given. We don't know this reference angle, but we do know this reference angle. Here's the thing. F2, because we don't know the angle, it could be anywhere. F2 could be over here. That could be F2. F2 could be over here. It could be here. It could be there. We don't know what angle, right? We do know that they wanted us to minimize F2. So we wanted F2 to be the smallest it could be. So that is a hint that F2 is actually directly vertical. So F2 is directly vertical in order to minimize that length. Do you see how the vertical would actually be the shortest length it could be? So in reality, we actually have a right triangle. Because they told us that FR was horizontal. They told us that F2 needed to be minimized, so that must be vertical. They gave us the hypotenuse of the triangle, 800 newtons. They gave us the reference angle, 60 degrees. Now what? Whoops. So let's make a note to minimize F2, make it vertical. What else can we label? Good, 30 degrees.
I had a question, Professor. So, are we able to use congruent angles on this one? And then, so the top is 60 above the angle we're trying to find?
Yes.
And then would that be like a 90 with F2? So like the angle would just be like 30 left over? Is that,
Yep.
is that, how, oh, okay.
Yeah, that
you.
works too. So that is one way to look at it. Another way to look at it is just to be, here we have a 90 degree, a right triangle, right? So all the angles have to add up to 180. So that's another way to find that 30. So either way would work. So you were referring to using alternate interior angles, essentially.
Correct.
Mm-hmm. Okay, so now that we have a right triangle, we could use like our sine, cosine, and tangent to solve for our unknowns. So for example, if I wanted to solve for F2, I could use sine of 60 is equal to what over what?
F2 over 800.
Good. What do you get for F2?
692.8
Units.
million.
And if I wanted to solve for FR, what should I do?
You could take a tangent of 30 is FR over F2,
Tangent of 30, F.
which are FR over 693. Okay.
Okay. What do you get?
$400 newtons.
Very good. So you could have done sine, you could have done cosine, tangent. You even could have done Pythagorean theorem because you had two sides of a triangle out of three, right? So you could have done a squared plus b squared equals c squared and solve for that unknown side. You could have done special triangles because it's a 30, 60, 90 triangle. So you could have used ratios to solve for that third side. There's a lot of different mathematical ways you could have done to solve for that third side. So for your final answers, you would want to say that F2 is, 693 newtons, but what direction is it in?
Is it 30 degrees?
So F2, looking at F2, it's vertical, right? Yeah,
Oh.
so, and it's pointing the way I drew it, pointing down. So F2 is directly down. And FR, its magnitude is 400 newtons. And what is its direction?
Horizontal.
Yeah, pointing directly to the right. So that's how you would give your final answers, is with a magnitude and a direction. This is your magnitude. This is your direction. Magnitude, direction.
Excuse me,
Yes.
Professor?
Question?
Yeah, for the previous answer, we put the angles. Can we just put the arrows for those answers instead of the angle?
Yeah, if it's directly up, down, left, right, then you can just put arrows. Or you could put the degrees. So you could have put 0 degrees and you could have put 270 degrees if you wanted. Right? But if it's up, down, left, right, you can go ahead and just draw an arrow. But if it's not perfectly, up, down, left, right, then you'll have to give the degrees.
Okay, thank you.
Mm-hmm. So just remember that math is not a spectator sport, right? It may seem easy while you're watching me do the algebra or watching me do the trig, but if you're not coming up with what to do next step by step by step, then that's a problem. So you need to try and do practice problems on your own, put pen to paper. You need to read the book. Not only do you need to come to class, you need to solve extra practice problems. There's so many practice problems in your book. There's like fundamental problems and preliminary problems and all sorts of problems you can do to kind of gear up to even be prepared to start your homework. Okay. So I would say to remind yourself to take a look at those preliminary problems in the book. It'll help you study and it'll help you be prepared to even just do the homework. And then after that, there's even ones that are called fundamental problems. So it's like, these are the fundamentals. You better be able to do this before you do the homework. take a look at those and practice those on your own.